Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, welcome to the final lecture in this room today. A little bit about what this all means. My name is Kenneth. I'm part of the Microsoft Research Program Management Team. And we have a small group of about 6 or 7 folks. And our role in life at Microsoft is to help transfer technology from the researchers and the research labs into the product groups. So if you have any questions about demos you've seen, things that have interested you, or something you've heard at a lecture, and want to find out more about how to integrate it into your particular area of products, give our alias a holler and we'll help you out best we can. The alias is MSRPM, and that link is good throughout the year. I'd like to introduce Byron Cook, who originally is from Redmond, but now kind of rides herd on the researchers at Cambridge, UK, keeps them in line. Byron had an article in Scientific American last December about Terminator, and that's part of what his talk is today on how to automatically prove correctness in concurrent programs. Byron?
Okay.
It's all yours.
Thanks very much. Okay, so what I wanted to do today was to talk not about the automatic formal verification tools for software that are available today, but to sort of try and forecast what will be available perhaps in a couple of years or so. So what I mean by automatic formal verification software, automatic formal verification tools for software are tools that take a piece of software and a property that's perhaps given to the tool by the user or some other tool, and then automatically tries to find a proof of correctness, right? So that's in contrast to tools that try and find bugs. So we're not necessarily finding bugs, we're trying to prove the absence of bugs. And I want to talk about those tools, what we might see in a couple of years. So to do that, we should look at what the frontier is for these kinds of tools. And I've struck something off the list. This is the thing that we've seen quite a bit of activity in for the past couple of years. So if you have a piece of software that's, say, under 50,000 lines of code, and you have a property that you would like to prove that's it's a safety property, and it's arithmetic, so something like if x is less than y at this particular program location, then this I would consider as something that there are now tools that can handle this, right? So I don't want to say it's a solved problem, but now there's a number of tools that you could try, and sometimes it'll work and sometimes it won't. So I'm going to say that that's not really on the frontier. What I'm actually talking about are tools that are problems that we don't really have tools for at all. Last year I gave a talk at TechFest on Terminator, which is a tool that automatically tries to prove liveness properties. So these are distinct from safety properties like is x less than y always is x always less than y at this location. A liveness property is more like if I call this function, will it always return control back to me? That's like termination. Or if I call this function, will I always eventually call this other function in my code? So these are examples of liveness properties. And this is a fairly new turn of events that allows us now to prove these sorts of properties automatically of software. But it only works for sequential programs. So if you have a concurrent program and you want to prove that your thread always eventually will terminate, then the tools that have been available don't solve this kind of problem. And the same goes for shape properties. So these are properties like, does x, which is a pointer, does it always point to a well-formed acyclic list, for example, or a well-formed doubly linked cyclic list? So it's a property not about arithmetic things like x and y and whether or not they're less than each other, but it's more about the shape of the data structures that the program is manipulating and constructing during execution. And again, there's been a couple of recent advances that allows us now to apply to prove these kinds of properties of sequential software, and those have come through in the past couple of years, but really nothing for concurrent programs. So the big item on the frontier is support for concurrent software. So if you have a concurrent piece of software that makes non-trivial use of data, so that is it has, I'm not talking about like a protocol with a few bits, but I'm talking about a concurrent program that's operating over the heap, for example, then to date we've really had nothing that can automatically prove properties of those programs, in particular for liveness and shape. And this is made particularly bad by the fact that people are programming more and more and more concurrent programs, right? So it's quite unusual nowadays for us within the company actually to write sequential software. Typically, there's some aspect of concurrent execution in the code that we write. So what I wanted to do today was to tell you about two lines of work that try and address this problem. So I'm going to tell you actually about two extensions to tools that I'm involved with. One is called Terminator, which is the thing I talked about last year and which is discussed in the Scientific American article. And then there's also a tool called Slayer. So, and in particular, I want to talk about extensions to these tools that allow us to handle concurrent programs. And in particular, there's a theme that runs through both of these extensions, and it's a theme of thread modular approaches. So the idea here is that, I mean, one way that we could prove a concurrent program correct is just to take all the threads, jam them all together, and then consider all possible interleavings between them. But that tends not to be very scalable. So what we do today is we just ignore the problem, right? So static driver verifier, for example, which is a tool that's shipped by the Windows division to verify Windows device drivers, just completely ignores the concurrency issue altogether. So it will miss bugs. It'll find a proof, if you will, of a device driver's correctness, but it could be that actually another thread could mess with some data structure that it's manipulating, and actually, so the proof is actually not really a proof, right? It's proved the correctness of a device driver in a sequential execution environment when device drivers actually run concurrently. So the thread modular approach is an approach where we try to take sequential tools for sequential programs, so proof tools for sequential programs, and run them only on one thread at a time, but then do it in such a way that we can reason about the correctness of the concurrent program as a whole. So the idea is we want to try and find a scalable solution where hopefully the sequential tools are scalable, and then we'll only apply it to one thread at a time, maybe a number of times, but we never consider all possible interleavings. And so that's sort of the theme of the day. So let's first look at this extension to Terminator. Okay, so this is the kind of thing we're trying to verify. Look at this code. This is from a keyboard device driver in Windows. And an important property of device drivers in Windows is that the dispatch routines that they export, so the event handling code, should always eventually return control back to the caller. Right, so it would be a real disaster so in this case, this is a keyboard device driver. So if you press a key, and then the event handling code that's handling that event, if it just handles the event forever, then the machine's going to lock up, right? So that's a disaster. So we need to prove that the thread that's handling the event will eventually terminate, or that is the thread makes a call to a function. That function should eventually return control back to the caller. In a concurrent environment. And to do so, we need to prove termination of things like this loop. Right? So this is a loop that operates over a queue. It's calling some routine keyboard class dequeue read by file object, which is pulling elements off some queue. And it will continue to pull elements off of that queue until the queue is empty, in which case then this API will return null. And in that case, then the hope is that we will eventually reach that case, and therefore the loop will terminate. Now, proving termination of this loop in a sequential environment is extremely easy, right? Because every time you pull an element off the queue, the size goes down a little bit. And so there's a ranking function that is like a witness to the proof of termination, which says that on every iteration of the loop, this rank goes down, right? And that is the size of the queue. And we know that when the rank finally hits 0, that the loop will terminate. And so that's how we would prove termination. And Terminator is a tool that automatically finds all the ranking functions and so on. We won't go into detail on that. But in the sequential environment, things get a little bit trickier. And that's because of this guy. Right? So we could go in a sequential environment and prove the termination of that loop and the window behind. But actually, in a concurrent environment, the thread in the window at the forefront is also executing, potentially, and potentially adding new elements into the queue at the same time. right? So if the frequency of the code in the window on the forefront is at the same or faster than the loop in the background, then the loop in the background won't terminate, and therefore the machine will hang. So it's this kind of thing that we have to actually consider when doing a termination proof. Now, if you look at in this particular case, it's fine, right? So you see why it's fine? It's fine because, in some sense, the lock that they're both acquiring is protecting the termination of the loop, right? I usually think of a lock as protecting data, but in this sense, it's actually protecting the termination argument in a way. So the termination argument is that the size of the queue will always go down on every iteration, but also that between every execution of an assignment or a conditional check inside the loop, that it's like between the steps, that the other threads executing in the system also won't increase the size, right? So that's actually the termination argument. And so the lock is in some sense making sure that that's true. So the other thread acquires the lock, and therefore it can't insert elements into the queue while the loop that's draining the queue is executing. And so in this case, it's okay. And this is the sort of thing that our extension to Terminator automatically finds. So it's basically doing this kind of reasoning. So as I said before, it's a Terminator implements a thread modular proof search. And the idea is to execute essentially Terminator on only one thread, right? One thread together with something called an environment abstraction. And the environment abstraction is some way you can think of it as all of the other threads in the system boil down to one thread. So it's a over approximation of the behavior of all the rest of the threads in the system. So no matter how many other threads there are, we want one single thread, if you will, but very non-deterministic thread that sort of captures all the behaviors of the other threads, and it can over approximate a little bit. It can do more, but it shouldn't do less. So what we're looking for is an environment abstraction. What's nice about this technique is that we remove all interleavings, right? We never consider thread 1 to thread 2 to thread 3 to thread 1 to thread 2. We just analyze thread 1 together with this sort of demonic other thread that we synthesize in some sense. And for that reason, it's quite scalable. The difficulty with these approaches, and it's been, I mean, thread modular approaches are not new, and what sort of most people in my field would say is that thread modular approaches often lead to very imprecise tools. So that is, often they're very scalable, but they often return false bugs. Right? And the difficulty, the reason that they would return false bugs is because the environment abstraction has to be right. You have to find the right environment abstraction. And then the space of the potential environment abstractions is huge. So if you don't have the right heuristic to find the environment abstraction that's going to work, then you're going to give a false answer. And so that's really the challenge in implementing a thread modular proof search. But we luck out in this particular case. So in this case, we're very, very lucky. There's a heuristic that for coarse-grained concurrent programs seems to actually work out remarkably well. And in experiments with device drivers, the accuracy was pretty amazing. So the insight is as follows. So we're trying to prove termination of a thread. We don't care about the other thread. So we don't care about proving termination of the whole program. We just consider proving termination of one thread in some concurrent execution environment. You can actually, for the most part, synthesize an environment. I'm going to show you an example of this, so just bear with me. But you can find an environment abstraction by just looking at thread 1. So imagine proving termination of a loop, finding out the reason why it terminates, and the core reason as to why it terminates, which is computed by the termination proof engine, will actually tell you what it is you expect of the environment. And then you just go and make sure the environment respects that. So let me show you an example. Okay, so here I have 3 threads. We want to prove termination of thread 1. And non-det is something I use quite a bit. This is non-deterministic choice. Right? So this isn't something you can write in C, but you can abstract a program using non-det. So if you see x less than y, you could replace it with non-det, and now it just allows more behaviors. So think of non-det as every time you hit non-det, we just make a non-deterministic choice, and our proof of correctness has to be sound with respect to all possible potential choices the non-det could make. So notice that, for example, T2 doesn't terminate. right? Because non-det could always return true. But thread 1 might terminate. Does it terminate, by the way? Someone have an answer? Yes, good answer. It should. So let me try and explain why it terminates first by just explaining why it would terminate if there weren't thread 2 and thread 3. Okay? So if there weren't thread 2 and thread 3, then imagine that x, so we don't know what the value of x is when we start the loop. So imagine that x is negative. Then we're not going to go into the loop, and therefore we terminate, right? So the only case we have to worry about is when it's positive. Okay, so imagine it's positive. Then on every iteration of the loop, x is going to go down. And so eventually, we're going to hit 0, in which case we'll terminate. Okay, so the ranking, so terminator would prove termination of this. And the ranking function in this simple case would be very simple. So the ranking function would be x. Right? X is the ranking function. That is, it's the thing that on every iteration goes down, the valuation of it. So if you look at x before the loop body and then execute the loop body once and look at x again, the value will go down. Right? And we also know that x is always supposed to be positive. And for that reason, we know it will terminate. So that's the ranking function is x, and it's like the witness to the proof. Okay? All right, so what we could actually do is say the environment abstraction is this, as follows. So I'm using x prime to mean the next value of x. Okay? So it says that in the environment, whenever the environment makes a step, it has to at least reduce x or leave it alone. Right? No matter what the environment does, allow any instruction from the environment. Just take any assignment statement from thread 2 or thread 3. So long as x at least doesn't go up, it's fine. Right? And this is enough to guarantee termination. If thread 2 and thread 3 respect this environment abstraction, then that's sufficient. Okay, so now all we have to do is check that thread 2 and thread 3 respect this. Right? So we look at first instruction 2 of thread 2. So it's saying x prime needs to be less than or equal to x. So after the call to interlock to decrement to x, x will be 1 less than it was before. So it respects the environment abstraction. So that's fine. Look at the assignment at line 2 of thread 3. So there, that's actually modifying y. So that's fine. So it's leaving x alone. Look at the lock at thread 3, line 3. Is just a call to lock, so that won't affect x. But line 4 gets us in a little bit of trouble, right? Because line 4 is saying we scramble x. We have no idea what this is doing. It could return anything. Maybe it's like scanf, right? If it's something from the user. We have no idea. So we can't guarantee now that x will always stay the same or go down. And in this case, actually, we can refine the environment model just a little bit by if we model locks as integer valued variables and ownership as the thread ID being in the variable, then we could say, well, now the environment abstraction is either x doesn't go up or thread 3 owns the lock. Right? And you'll notice that we can figure that out actually from look at line 4 and look at what we know about the state of lock L at line 4. Right? So terminator, the refinement method then will figure out the context under which the assignment that doesn't respect the environment is, and we'll add that into the environment model. And so now actually this turns out to be enough to prove termination of thread 1. So with this environment model, if on every step between the assignment statements and conditional checks in thread 1, we have a demonic thread that at least respects this environment condition, but nothing more, then we can still prove termination of thread 1, and then thread 2 and thread 3 respect it, and so now we're done. So we found the environment model. And this is something that Terminator automatically computes now. Okay, so what we did is we took Terminator and we applied it to, 30 device drivers or so. And we found a number of correctness proofs. And finally, actually, so it's funny, in the Scientific American article about Terminator, the article's going along, and then right at the end, some pundit, someone from my field, points out that actually Terminator's proofs for concurrent, that it doesn't produce proofs for concurrent programs, right? So all this work we've been doing with device drivers was actually sort of fairly academic, right? But now, finally, we actually have termination proofs that are sound for device drivers if you ignore overflow. And we also found some bugs. So I thought I would show you an example. So this is from modem device driver, and it's in the IOCTL, the IO control dispatch routine of the modem device driver. And I'll show you what's happening. So the device driver first takes a lock, and then it's a loop that is, again, iterating over a list. And it keeps executing this loop until the list is empty. Okay, and as before, we see it's removing an element from the list. Okay, so that's fine. So every iteration it's removing the elements from the list, and it's doing under a lock. So presumably the other threads that might add elements into the queue would take the lock, so we're protected and we're fine. But the bug is here. So in the middle of the loop, it actually releases the lock, does presumably some expensive operation, and then reacquires the lock. Right? And so this is a little bit of a debacle, because now we have another thread that is trying to do the right thing. It acquires the lock. It adds an element in. It releases the lock. But now you can imagine cases where the thread on the left-hand side, if it runs a little bit slower than the calls to the dispatch routines on the right-hand side, then you can imagine a case where the thread on the left-hand side isn't able to terminate, and therefore the modem's hung. Okay, so that was the termination work. So now we'll go to the concurrency, to the shape property work. And the themes are sort of similar, but the details are a little bit different. So what is it we're trying to prove, first of all? So this is, we're trying to prove things like this. Is list head always at this program location, whenever we hit this program location in the execution of the program, is it always a pointer to a well-formed cyclic doubly linked list? Right? So that's the sort of thing we might want to prove. Okay? And only recently we've been able to prove these kinds of things automatically of programs. And a tool that I've been involved with Josh Burdine is a tool called Slayer. And this tool is based on something called abstract interpretation. So what Slayer does is it actually symbolically executes your program. Right? So it's not concrete execution where you know the exact details of the RAM and the registers and so on, but it's actually we build a symbolic representation of the heap, symbolic representation of the valuations, and we symbolically execute the program. And what we do is at certain critical points we do something called a widening, where we lose some information. So our goal is to over-approximate all possible reachable states of the program, and hopefully we won't over-approximate too much. So what it does is it analyzes your program, symbolically executes it, and it always reaches termination because we do some widenings, which allows us to not have to execute the loop forever, loops forever. And then when we're done executing the program symbolically, we actually can tell you a set of facts about your program. So at every location, we tell you about the layout of the heap at that location of the program, and we can prove memory safety, and we can prove absence of memory leaks and so on. And up until now, Slayer and tools like it have only worked for sequential programs. So the new work is to use thread modular techniques. So this is the same slide as before. We want to implement a thread modular technique. The great thing about thread modular techniques is they're scalable. The horrible thing about thread modular techniques is that you have to find an environment abstraction, and the space is big, and so you have to find a heuristic that will allow it to work in the cases you're hoping it to get it to work. And in this case, we again luck out. So what we're going to do in this case is we're going to trick the shape analysis, this tool that is analyzing sequential programs. We're going to trick it into computing something called spatial resource invariants, and this comes from the literature. These spatial resource invariants form in some sense, the environment abstraction. So let me try and tell you what a spatial resource invariant is. So imagine that we take in our abstract interpretation, or our symbolic execution of the program, we maintain some different buckets of thread local versus shared heap. Right? So imagine we have 3 threads, and in the blue, green, and yellow bucket, we keep the heap that we know is only reachable via those threads. And then the red circle represents the shared heap, so the heap that's actually reachable by one or more threads. And what a spatial resource invariant is that for each lock, we associate a description of a shape of the heap that lock protects. Okay? So imagine that we have one lock, so we only have one spatial resource invariant, and that spatial resource invariant is the inner circle. And the inner circle for the lock says this shape, and the description of the shape can be somewhat abstract. So it can be like trees pointed to by X, or lists of unknown length pointed to by this stack variable, for example. But it's a description of what data structure is protected by this lock. Okay? And then in our abstract interpretation, we're only going to analyze one thread at a time. But when we're analyzing the thread, when we call a lock, there's a special thing that happens. And that special thing is a symbolic representation of that shape suddenly magically shows up in the heap of the thread local heap. And then when we release the lock, then the abstract interpretation in the symbolic representation of the heap, has to find that same shape and remove it, nuke it. Okay? So let's see if I can show you an example. First, let me just talk a little bit about the strategy that it implements. So what we're going to do, what the tool does is it starts off using some other tools. It starts off with a guess of the spatial resource invariant for each lock. So for each lock, we just give it a sort of a guess as to what the spatial resource invariant might be. And then we run the sequential shape analysis on each thread. And how the shape analysis might fail is when we take a lock, we get some a shape, and then we do some mutation on it, and then when we try and put it back, it's not the same shape. And in that case, then it's not what I said was that it has to be the same shape, right? So if in that case it fails, then we refine the resource invariant and try again. So I'll show you an example of a resource invariant that works. But an important point I wanted to make is that when we call unlock, one thing we do is we try and generalize. So we might take we take a list of length 5 and we will generalize it and say, well, it's any list of any length. I don't know. Okay, so that's a sort of an important point. You'll see why in a moment. Okay, so this is do we have 2 threads? Right? Is this memory safe, by the way? So that is, will any dereference crash? Yeah, I don't think so, by the way, but we'll see. Okay, let me. So what we're going we have one lock called LK, and we're going to we have a resource invariant that we start off with. So I've already done the refinement, so I'm just going to show you the final step. So this is the resource invariant, and this is a visual description of a list pointed to by H of length 1 or more. Right? So that is, H points to a struct, and the next field of the struct points to a list of some unknown size, and the ... means unknown size. And it eventually goes to null. So it's an acyclic list. Okay, so now remember we're doing a thread modular technique, so we're going to only analyze one thread at a time using this resource invariant. We only have one lock, so we only need to run resource invariant. So we'll start off the execution, say, right before the call to lock. And I'm going to use the blue rectangle on the right-hand side to represent the shape of the heap when we got to this location. It's symbolic, so I'm just going to say, I don't know what it is, but I'll represent it with that box. Okay? And if we need to know more about it, then we can investigate further. So when we call lock, then the resource invariant shows up into our heap. So now it's a part of our local heap. And then when we execute the instructions, like the malloc and the pointer swings and so on, then right before we call unlock, now we have a list of size 2, right? H points to the same struct as before, but the next field now points to a new struct that was malloced. X points to that struct, and then its next pointer points to a list of unknown length that eventually goes to null. Okay? Now, they don't match up, right? Because when we call unlock, we want to take the same shape. We want to symbolically have a picture that's the same shape as we had before, and then we want to nuke it. And if we can't do that, then we have decided we have failed. Okay, so what we'll actually do is we'll generalize. This is a list of length 2. What's more general than a list of length 2? List of length 2 or more? It's a list of length 1 or more, right? So if you have the list of length, all lists of length 2 or more, then the lists of length 1 or more cover all of those. So it's a generalization. So it's sound to say, oh, okay, well, we'll generalize that and make it to a list of length 1 or more. And now they match up. So now when we call unlock, we can nuke it. Right? And now we're left with the same state as we had before. And then the analysis continues on. And it actually turns out that we don't have to run the analysis anymore because the state before and after the execution of the loop body is the same. So going again isn't going to give us any new answer. So we've actually reached a stable point. And in this sense, we don't need to execute it anymore. And whatever is in that blue box, the shapes that are drawn and so on, that is the representation of the heap in the program. Okay, now we'll go to the other one. So again, the same thing. We start off with a symbolic representation of the heap. We get the resource invariant. Now we actually have two cases. There's a conditional. So we could go through one of two cases. So we actually have two states, and they're represented in the two clouds. The one is the case where essentially the list was of length 2 or more. So we did this conditional check to ask, is y equal to null? If it's not equal to null, then it's of length 2. And we remove one of the elements, free it, and then come back. So now, on the left-hand side, we're in the state where h points to a list of length 1 or more. And on the top side, that's the case where we don't go into the conditional. Right? So y was equal to null. And in that case, the list was of length exactly 1. Right? Because h pointed to a struct, and its next field pointed to null, so it was a list of length 1. And again, we're in the case where we want to generalize. Right? Because now we're supposed to call unlock, and we generalize, and we can actually generalize sets of these abstract heaps. So we can again say, what's a generalization of a list of length 1, exactly 1, or a list of length 1 or more? Well, that's list of length 1 or more. So we generalize again, and again, they match, so we get to nuke the resource invariant. And again, the states are the same. So now we're actually done. Right? And it turns, it's a little bit magical, but actually we found a proof. So it turns out that the resource invariant of the lock LK protect lists from H to null of length greater than 1 is the resource invariant. And you can look in the literature and find something called concurrent separation logic, which tells you if you find a spatial resource invariant, if you prove that using that spatial resource invariant in the way that we did, that the program doesn't crash on each thread at a time, that you actually now have proved memory safety of the whole program, of the concurrent execution. And that's pretty neat. Okay, so how am I doing for time? All right. Okay, so let me say a few final words. So what were we doing? So we were taking sequential analysis tools, like sequential termination provers or sequential shape analysis tools, and we're trying to actually make them work for concurrent programs, because concurrent programs are actually the thing that we're all interested in, right? If we write real software that we sell, typically we write concurrent software. And so the strategy that in the research community we've taken for a long time of essentially ignoring concurrent programs and focusing our attention on sequential programs is interesting and it's useful, but it's sort of not really solving the problem that we have at hand, right? So ignoring concurrency is unsound, right? You can prove the memory safety or termination of a loop, and actually on the machine it's not going to terminate, or it won't be memory safe because of some interaction with some other thread. The other possibility is to consider all possible interleavings and just build a sequential program that represents all possible interleavings of the concurrent program, but that turns out to be wildly unscalable. So that's not going to work. And there are some techniques that people have worked on to try and reduce, but not completely eliminate, the number of interleavings that are considered. And that's actually a less scalable but more accurate method. So if we can find a thread modular method in which we find a heuristic that seems to work for the programs that we're operating on, then that's actually a much more scalable approach. But of course, you have to find that heuristic. So what's been neat about this work is that we have sort of some tricks that work for us. Let me tell you what's not working, right? So first of all, I've only talked about coarse-grained concurrency, right? And I think many of us actually do fine-grained concurrency, right? So my tools don't work for fine-grained concurrency currently, and there's some ideas, we're working on stuff, but that's much further out. So we'll see how that goes. So really, sort of coarse-grained concurrency where the locks are all globals, or the locks, or there's a finite number of locks in the heap, but you can sort of analyze the program fairly quickly and figure out which locks are going to be used. That's the sort of thing that we're talking about. So for example, programs where the locks are stuffed in a list, then the techniques I've been talking about aren't going to work. We also have been fairly naive about memory models, right? And so in concurrency, this becomes extremely important. So this is something that that the proofs are sort of missing bugs and real executing software, because the notion of the memory model is quite weak. And also, this work has only really treated one locking idiom, and that is lock, right? It's not, we're not treating mutex and so on. So programs that use other locking idioms, it's sort of future work to support these methods, but that's probably not too big a deal. So I promised a sort of a glimpse into the future, right? And I think that in the next couple coming years, it's possible that we could see, depending on how it goes for ramping up the analysis for sequential software, that we know of techniques now that for termination and for shape, at least, that would allow us to automatically prove interesting properties of coarse-grained concurrent programs. And that's actually an interesting application, because there are classes of software that only use coarse-grained concurrency. For example, it's extremely unusual to see fine-grained concurrency in device drivers, for example. And device drivers are are a class of fairly buggy programs that hurt us as a company. And the trend is, for scalability, is to use thread modular techniques together with sequential analyses and some tricks that allow us to automate the construction of abstraction environments. So for us, in termination, it was this idea of looking at the potential counterexamples to termination only in thread 1, or only in the thread we're trying to prove terminating, and essentially synthesizing an environment abstraction irregardless of what the other threads are doing. Right? And for shape, the idea was to associate with each lock a formula. I drew it as a picture, but it's actually in the analysis. It's a mathematical formula that describes the shape in the heap that's being protected by the lock, and to actually use, in some sense, counterexample guided abstraction refinement techniques to start off with a guess, run the analysis, it fails, look at why it fails, refine the resource invariant, and then try again, and to come up with a stable state, right? A set of resource invariants that are enough, such that then we can reason that the program is memory safe. And for safety, actually, thread modular techniques haven't been as popular. This is for standard safety, like if you want to prove that at this location X is always less than Y, but in a concurrent environment, and the techniques for finding environment abstractions there have been some publications, but when you talk to people individually, they're not overly happy with them. So actually, it seems like for termination and shape, we sort of luck out, whereas for standard safety, maybe it's a little bit harder, but we'll see. So the experimental results are promising. There's research papers you can look up if you want to know what they are. Number of correctness proofs found, real bugs found, both in shape and in termination. But the tools that I used for experimentation are a little bit too preliminary just to send you a URL, right? So I'm happy to work with you, but you should email me if you want to become an early adopter. So there's my email address. If you want to know more information about Terminator, you can go to the Terminator website. In about 3 weeks, we'll put up a paper that will appear at a conference called PLDI, which is about this extension that I told you about for Terminator concurrency. If you want to know more about Slayer, you can go to the Slayer website, and actually, ironically, it's the same thing. So we actually have a paper that will appear, another paper that will appear at this conference PLDI, and in about 3 weeks, we'll put it up on the website that describes the extension I told you about in a lot more detail. And you can find out information about me at this website, and should be at the Speaker's Corner afterwards. And so that concludes my talk. Thanks very much.
We've got a few minutes for questions, and then at 1:45 we'll stop and evacuate the room. If you want to talk to Brian some more, the Speaker's Corner he's referring to is out the door to the right at the end of the hall, and you can chat at length there. Any questions? Raise your hand and we'll bring you a mic.
Thank you. Hi. In the slide of removing an item from the list, okay, I don't understand how they match. The data structure match, especially if you don't have like h equal y at the end before the unlock.
Oh, so it's in this example here? Could be a bug in my code.
Okay.
Sorry. H. Okay, so what's your question again? Say it.
Okay. I don't understand. You said that the resource invariant match. I don't know how they match, and during the omission of h equal y also.
Maybe we should take this offline and talk about it on my laptop.
And the second question is about the ranking function in Terminator.
Yep.
How do you guarantee it's a monotonically decrementing function?
So
monotonically decreasing function. Sorry.
So how do you guarantee that it's always
Yes.
being done? So that's actually a condition that's checked. So Terminator synthesizes a ranking function and then actually proves that always goes down. So it's a subject of a whole different talk. Just talk about how we do that. But we have an automatic method of doing it basically, and that was actually the subject of a TechFest talk I gave last year, which is online.
Hi. So what does a shape bug look like?
Oh, shape bug. So for example, there was one where, let's see, how does this work? A device driver had it's a little bit hard to explain. There was a case where essentially it was dereferencing a pointer that didn't exist in the case that you had an empty list. So a cyclic empty list is represented as a single node where the forward and back pointer point back both to it. And there was a case where they were doing some casting that only really worked in the case that you had a non-empty list.
Actually, I have another question then. So in that case, the resource invariant wasn't what was required by the function. Is that, I guess, how you would say?
So that was actually a case that would have been found with sequential also.
Oh, okay.
Yeah. But I mean, the case that you in concurrency, you can imagine. I mean, you could pretty easily mess this up, right? Yeah. I mean, you could create a tree and then unlock. So, and then you don't know if so if you created a tree or you made the pointer point to something that wasn't a list at all, and then the guy on the left starts dereferencing that, then you're in trouble.
Ed, and if you got more questions or want to discuss with Byron down at Speaker's Corners, thank you for coming. Thanks for coming to TechFest.